In my last video, Indeterminate Forms Part 1, L'Hopital's Rule, we have seen if FA equals GA equals 0, then how we can find limit of a rational function, limit fx upon gx as x tends to a as limit f dash x upon g dash x as x tends to a, which is known as L'Hopital's rule, and this particular form is known as indeterminate form of the type 0 upon 0. In this video, we will study indeterminate form infinity upon infinity, which by certain adjustments can be transformed into indeterminate form 0 upon 0 and can be easily solved by L'Hopital's rule. Let us see how. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. If limit of x as x tends to a is infinity and limit gx as x tends to a is also infinity, then limit fx upon gx as x tends to a will be an indeterminate form of the type infinity upon infinity. Let this limit be a finite limit L. We will find out what will be limit f dash x upon g dash x as x tends to a. Since limit in 1 being an indeterminate form infinity upon infinity, we will write it as L equals limit 1 upon gx upon 1 upon fx as x tends to a, so it gets transformed into indeterminate form 0 upon 0. Because 1 upon infinity is 0, 1 upon infinity is 0. By L'Hopital's rule, L will be limit derivative of 1 upon gx minus 1 upon gx whole square into g dash x upon minus 1 upon fx square into f dash x as x tends to a, because we know d by dx of 1 upon x is minus 1 upon x square. This will be limit fx upon gx whole square as x tends to a into limit g dash x upon f dash x as x tends to a, which is L square into limit g dash x upon f dash x as x tends to a, which is L. This gives limit f dash x upon g dash x as x tends to a equals L square upon L. But since L is a finite limit, it will be L. Let us name this 2. So from 1 and 2, we can write limit fx upon gx as x tends to a is limit f dash x upon g dash x as x tends to a. So for a finite limit L, this statement 3 is same as we use for indeterminate form 0 upon 0. So if the given form is like this, we can convert it into indeterminate form 0 upon 0 by writing it as limit 1 upon gx upon 1 upon fx as x tends to a, and then differentiating, we get limit like we get here in expression 3. Let us evaluate limit tan x log x as x tends to 0. Here tan 0 is 0 and log 0 is infinity. We can write this limit as limit log x upon cot x as x tends to 0. This is infinity upon infinity indeterminate form. We have seen if the form is infinity upon infinity, we can directly apply L'Hopital's rule. So by L'Hopital's rule, it will be limit x tends to 0 of derivative of log x 1 upon x upon derivative of cot x minus cosec square x. This will be minus limit x tends to 0. We will write it as sin square x upon x. Again by applying L'Hopital's rule, it will be derivative of sin square x 2 sin x cos x upon derivative of x 1. After taking limit, this will be minus 2 sin 0 cos 0, which will be 0. So the limit is 0. Evaluate limit as x tends to 0 log sin x upon log x. Here sin 0 is 0 and log 0 is infinity and log 0 is infinity. So this is an infinity upon infinity indeterminate form. We will apply L'Hopital's rule and write limit x tends to 0 derivative of log sin x 1 upon sin x into cos x upon derivative of log x 1 upon x, which is limit cos x as x tends to 0 upon limit sin x upon x as x tends to 0, which is after taking limits cos 0 upon 1. So the limit is 1. Evaluate limit log sin 2x base sin x as x tends to 0, which equals limit as x tends to 0. Here we have to change the base, so it will be log sin 2x base e upon log sin x base e, which is limit as x tends to 0. Here sin 0 is 0 and log 0 is infinity. Here also sin 0 is 0 and log 0 is infinity. So this is infinity upon infinity indeterminate form. We will apply L'Hopital's rule. Derivative of log sin 2x 1 upon sin 2x into cos 2x into 2 upon derivative of log sin x 1 upon sin x cos x, which is limit x tends to 0 2 cot 2x upon cot x. This again is infinity upon infinity indeterminate form. This we write as 2 limit x tends to 0 tan x upon tan 2x. This now is 0 upon 0 indeterminate form. We can apply L'Hopital's rule and it will be 2 limit x tends to 0 derivative of tan x sec square x upon derivative of tan 2x sec square 2x into 2. This 2 cancels with this 2 and we have limit as x tends to 0 of cos square 2x upon cos square x. Taking limit, this will be 1 square upon 1, 1. So this is the value of the limit, 1. Evaluate limit tan x upon tan 3x as x tends to pi by 2. Tan pi by 2 is infinity and tan 3 pi by 2 is also infinity. So this is infinity upon infinity indeterminate form. We will adjust the terms and write cot 3x upon cot x. Cot 3 pi by 2 is 0 and cot pi by 2 is also 0. So this is 0 upon 0 indeterminate form. Now we can apply L'Hopital's rule and write derivative of cos 3x minus cosec square 3x into 3 upon derivative of cot x minus cosec square x. We will rewrite this as sin square x upon sin square 3x. By taking limits, this will be 3 sin square pi by 2 upon sin square 3 pi by 2. This will be 3 times 1 square upon 1 square 3. So this is the value of the limit. Evaluate limit x raised to m upon e raised to x as x tends to infinity, where m is positive. As x tends to infinity raised to m is infinity and e raised to infinity is also infinity. So this is infinity upon infinity indeterminate form. We can apply L'Hopital's rule here. So it will be derivative of x raised to m x raised to m minus 1, derivative of e raised to x. This again is infinity upon infinity indeterminate form. We will again apply L'Hopital's rule and it will be m into m minus 1 into x raised to m minus 2 after writing derivative of the numerator upon derivative of e raised to x. We can go on and this will be finally numerator will be m factorial upon e raised to infinity will be infinity, which is 0 into m factorial 0. So this is the value of the limit. Evaluate limit as x tends to infinity of 1 square plus 2 square plus 3 square plus so on and so forth plus x square upon x cube. As x tends to infinity, numerator tends to infinity and denominator also tends to infinity. So this is infinity upon infinity indeterminate form. In the numerator there is sum of squares of first x natural numbers, which will be x into x plus 1 into 2x plus 1 upon 6 into this x cube. Limit as x tends to infinity. Numerator after simplification will be 2x cube plus 3x square plus x upon 6x cube. This is infinity upon infinity indeterminate form. So we can apply L'Hopital's rule to get 6x square plus 6x plus 1 upon 18x square. This again is infinity upon infinity form. Applying L'Hopital's rule, again 12x plus 6 upon 36x. This again is infinity upon infinity form. Applying L'Hopital's rule, derivative of 12x plus 6, 12, derivative of 36x, 36. This will be 12 upon 36, 1 upon 3. So this is the value of the limit. Evaluate limit 1 plus 2 plus 3 plus so on and so forth plus x upon x square as x tends to infinity. As x tends to infinity, numerator will tend to infinity and denominator will also tend to infinity. So this is infinity upon infinity indeterminate form. In the numerator there is sum of first x terms of natural numbers, which will be x into x plus 1 upon 2 into this x square, which is limit as x tends to infinity. X square plus x upon 2x square. This is also infinity upon infinity indeterminate form. We will apply L'Hopital's rule that gives us limit x tends to infinity, derivative of numerator 2x plus 1 upon derivative of denominator 4x. This is also infinity upon infinity indeterminate form that gives us by applying L'Hopital's rule again. This will be after taking derivative 2 upon 4. So the limit will be 2 upon 4, 1 upon 2. This is the value of the limit. Evaluate limit e raised to 1 upon x plus e raised to 2 upon x plus so on and so forth plus e raised to x upon x as x tends to infinity. Numerator is sum of x terms of a GP geometric progression where first term a is e raised to 1 upon x and common ratio r is e raised to 2 upon x upon e raised to 1 upon x, which is e raised to 1 upon x. Now we know that for a GP geometric progression, sum of x terms will be a first term into r raised to x minus 1 upon r minus 1. So therefore this will be limit x tends to infinity of, in the numerator we write e raised to 1 upon x into e raised to 1 upon x raised to x minus 1 upon e raised to 1 upon x minus 1 into 1 upon this x, which is limit as x tends to infinity e raised to 1 upon x into e minus 1 after cancelling this x upon x into e raised to 1 upon x minus 1. This will be e raised to 1 upon x into e minus 1 upon x into, for this e raised to 1 upon x, we will write expansion of e raised to 1 upon x, that will be 1 plus 1 upon x plus 1 upon x square into 2 factorial plus 1 upon x cube into 3 factorial plus so on and so forth minus this minus 1. This will be e raised to 1 upon x into e minus 1 upon this 1 minus 1 is 0, and after opening the bracket this will be 1 plus 1 upon 2x plus 1 upon 6x square plus so on and so forth. By taking limit, this will be e raised to 1 upon infinity is e raised to 0 into e minus 1 upon 1 plus 1 upon infinity plus 1 upon infinity plus so on and so forth. This is 1 into e minus 1 upon 1 plus 0, which is e minus 1. So this is the value of the limit. This expansion of e raised to 1 upon x is according to the expansion of e raised to x, which is 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus so on and so forth up to infinity. Evaluate limit x tends to a log x minus a upon log e raised to x minus e raised to a. As x tends to a, x minus a will be 0 and log 0 is infinity. As x tends to a, e raised to x minus e raised to a will be e raised to a minus e raised to a 0 and log 0 is infinity. So this is an infinity upon infinity indeterminate form. We will apply L'Hopital's rule and write derivative of log x minus a is 1 upon x minus a upon derivative of log e raised to x minus e raised to a is 1 upon e raised to x minus e raised to a into e raised to x, which is e raised to x minus e raised to a upon e raised to x into x minus a. This is 0 upon 0 indeterminate form. So we will apply L'Hopital's rule and solve it. Limit x tends to a derivative of numerator e raised to x minus 0 upon derivative of denominator e raised to x into 1 minus x minus a into e raised to x after applying product rule of derivatives. This is e raised to x upon e raised to x minus e raised to x into x minus a. After taking limit, this will be e raised to a upon e raised to a minus e raised to a into 0, e raised to a upon e raised to a 1. So this is the value of the limit. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Subscribe to this channel. Post your constructive comments to make the videos better. See you in the next video. Until then, keep watching Number Collage. Thank you.